Hi everyone, I'm Felipe del Rio from Universidad Católica and today I'm happy to present our work, Data Distributional Properties as Inductive Bias for Systematic Generalization. Today's model often struggle with systematic generalization. Even large language models have trouble handling rare concept combinations. For example, if you ask ChatGPT to generate a full cup of wine, it typically produces the most common form of a cup of wine, a cup that isn't completely full. To help address this issue, we focus on a simple but crucial question. Which data distributional properties help models acquire systematic generalization? And to answer this, we explore whether simply changing the training data itself can lead to better generalization. We built a multimodal masked language modeling task and trained a transformer encoder to process both an image and a text that describes it. We asked the model to predict an object's attribute by masking them in the text. For the data, we built on top of the Clever Cogent benchmark, a dataset of images with 3D geometric objects. Critically, some shape-color combinations are held out for out-of-distribution testing, letting us measure how well the model generalizes to them. Let's start by seeing what happens when we change the diversity of the training data. We increase the number of colors in the datasets from 8 up to more than 200. The results: the model ability to generalize to the new combinations improved consistently, with shapes prediction accuracy increasing by 89% points. This suggests that simply adding diversity promotes a disentangling inductive bias that boosts generalization. Next, we explore two other ways to change the data distribution: burstiness and latent intervention. Burstiness limits how many values of a given attribute, like color, appears together in an image. This creates scenes where only a few colors dominate, while other scenes focus on different colors. Latent intervention takes another approach. Here we directly alter the values of latent attributes like color across all objects in an image, while keeping everything else constant, much like causal intervention. We found that both of these properties improve out-of-distributional generalization in some scenarios. Though the gains are smaller than with diversity, these properties complement its effect. Together, they show that just changing how training data is structured can significantly improve model generalization. But what's behind with this diversity-driven boost in performance? We wanted to understand the mechanism. First, we tested whether it's just a matter of model capacity. But different model size didn't explain the improvements. Next, we measured classical disentangled metrics like DCI. While diversity did improve how disentangled the model encodes shapes, it decreased for color, so that wasn't the full explanation. Finally, we investigate shortcut learning. Using the normalized mutual information, or NMI for short, we measure how informative color is for predicting shape. We found that lower NMI correlates with better generalization. Interestingly, even when datasets that had the same NMI, more diverse data still led to better generalization. So far, we focus on data properties. To dig deeper, we explore how these reshape the geometry of the learned representations, leading to systematic generalization. For this, we measure the parallelism score, or P-score, a metric inspired by neuroscience. We compare pairs of representation that differ in just one factor, like shape. By subtracting these pairs and measuring how parallel these different vectors were, we quantify how consistently the model encodes that factor. A high P-score means the model encodes that factor in the same direction across different contexts. This parallelism is believed to be the key of generalizing by analogy. When we compare P-score to out-of-distribution generalization, we found a strong positive correlation. This suggests that more parallel representation and geometry is linked to better generalization. Interestingly, we also saw that datasets with lower NMI produce models with higher P-scores. This suggests a chain effect. Lower NMI leads to more parallel representations, which in turn leads to stronger systematic generalization. Altogether, this showed that increasing diversity doesn't just add variety, it fundamentally reshapes how models encode concepts, making them more robust to novel combinations. To sum up, here's what we found. Diversity, burstiness, and latent intervention each promote systematic generalization in a multimodal masked language modeling task. Diversity improves generalization beyond what's explained by reduced NMI alone, And NMI promotes systematic generalization by promoting the emergence of representation with more parallelism under attribute changes. In the end, we find that the dataset distribution itself can reshape the geometry of algorithmic representations, giving us a powerful new way to understand how models can generalize flexibly and robustly, much like humans do.